we've got effusion, diffusion, and Graham's law. Diffusion, you should already be, ladies, gentlemen, thank you for dialing in. Thank you for putting your phones away and getting your note sheets out. You can leave your calculators out, we'll be using them in just a moment. So, today's focus is going to be on diffusion, effusion, and Graham's law, which is going to be the relationship between the diffusion and effusion rates of different gases. So I got just a short video clip to show you to illustrate what Graham's law kind of looks like. Let's just do this guy. That's not working, so let's do this guy. Boom.
Students obtain ammonia and hydrochloric acid solutions on the end of Q-tips, place them into the straw, which is taped to their table to anchor it down.
All right, so what he just said at the very beginning of the video clip is that students take a Q-tip that has been dipped in hydrochloric acid and a Q-tip that's been dipped in ammonia, and they put it in opposite ends of a straw. The straw has been taped down to the table. There's a little black mark in the center to indicate where the center position is. And then you just sit and watch with bated breath.
As we watch, we will notice that the two gases, as they diffuse through the straw, will begin to make a very faint line just to the left of that midline. And as you can see there, the line is appearing as the two gases combine together into ammonium chloride, which is the precipitate of the two gases of ammonium and hydrochloric acid.
So that's where the two gases are meeting.
So the question now becomes, why is the line to the right of that midpoint?
Well, it's to the right because he turned it around and started looking from the other direction, that's why. But before, it was over here on the hydrochloric acid side, so we were filming from this direction before. Now he's filming from that direction, which is why the line's on this side rather than that side. But the hydrochloric acid was on the left, now it's on the right. The question really is, why is it not in the middle? So we should try to answer that. It would be fun to answer that in a strong accent. So let's do that here and here.
The particles in a gas move rapidly.
All right, so there's the strong accent. It's going to become a distraction, and it's fine, but I don't know whether it's the lady that's speaking. I don't know if she's recording this as she's driving down the road with her windows open, or if she's just breathing deeply into the microphone, or if somebody else is, like, I mean, it's an animation, so I don't think somebody else is filming while she's talking, but there's a lot of breathing going on. So please try to stay focused on the message.
Randomly on all direction. This helps to explain why diffusion takes place in gases. Let us proceed. Soak a piece of cotton wool in ammonia solution, and this provides ammonia gas. Also, soak a piece of cotton wool in hydrochloric acid solution. This provides hydrogen chloride gas. Now plug these two cotton wools in two ends of a hollow glass tube.
I think it gets
Cork
worse.
both ends, and you will notice that in less than a minute, a white ring begins to form. This white ring is in fact a dense white solid formed by the diffusion of two gases, ammonia and hydrogen chloride. Did you notice that the white ring is formed closer to the hydrogen chloride end? So can you tell which gas traveled faster? Is it ammonia gas or is it the hydrogen chloride gas? That's true, it's ammonia gas. The distance between the cotton wool soaked in ammonia gas and the dense white ring is greater than that between the cotton wool soaked in hydrochloric acid and the dense white ring. From this experiment, we can conclude that ammonia gas covered a greater distance inside the tube.
All right, so that's good stuff there. Okay, so that little experiment in the animation illustrated the differences in the diffusion rates of different gases. That's what our focus is on today. We're going to remind you what diffusion and effusion both are, and then we're going to talk about how to quantitatively relate the rates, or how fast these gases travel. So here's our diffusion. Diffusion, again, is the ability of gases to mix or to spread out and fill their entire container. In the video clip, that first one, well, in the animation for that matter as well, the line was where those two gases initially met. And because when you mix them, they form a precipitate. That's where you formed that little white cloud. But it wasn't in the middle because both of those gases weren't traveling at the same rate. So diffusion is how they spread out and they mix. Effusion is their ability to move through small openings or tiny little holes. And we talked about that when we first introduced this gas unit in terms of the kinetic molecular theory and then how fast they're moving, and ultimately related effusion to balloons and the fact that your typical latex balloons are pretty good at holding the air that you breathe into them, but they're not nearly as good at holding helium gas. They're going to deflate much quicker if they've got helium gas in them, because even though they look like they're solid, the latex has tiny little openings, and the helium, being a smaller molecule, squeezes through those openings a lot quicker than the carbon dioxide and oxygen and nitrogen that's in the air that we breathe. So our focus today is to talk about the rate or the speed of these processes. And the speed is going to be related to the kinetic energy. If you recall from a couple of weeks ago, the equation for kinetic energy is 1/2 mass times velocity squared. So the amount of kinetic energy that an object possesses, these little molecules, is dependent on both how big they are, how much mass they have, and how fast they're moving. Temperature is actually defined as the average kinetic energy per molecule in a sample. So if we got a sample of gas that is 273 Kelvin or 100 degrees Celsius, most of those molecules in that sample of gas are going to have the same amount of kinetic energy. There's going to be a few that have a little bit more and a few that have a little bit less, but most of them are going to have that same amount of kinetic energy that corresponds to 100 degrees Celsius. If we cut that temperature in half, which again is not 50 degrees Celsius, but it would be somewhere below zero, half of 273 Kelvin, then most of those molecules are going to have half of that kinetic energy. As a result, their temperature is going to be half as much. So at the same temperature, if we got two different gases that aren't the same mass, they're going to have to be moving at different velocities to have the same kinetic energy. Again, we got mass and velocity in our equation. So if the mass is bigger, the velocity of the bigger molecules is going to have to be a little bit less in order for the kinetic energy to be the same as a lighter molecule. So for a given kinetic energy, we got 1/2. If it's a big molecule, it's going to have a smaller velocity. For the kinetic energy to be the same for a smaller molecule, it's going to have a bigger kinetic energy. So as the mass goes up, the velocity goes down. They are inversely related. And again, this is for the kinetic energy to remain the same value. That's all good? Any questions so far? All right. So Graham's law quantifies that relationship with an equation. I'll show you that equation in just a moment. But all this says is the rate of diffusion, which is just another way of saying the speed or the velocity with which those molecules move, is inversely related to the square root of the molar mass. So V is going to be proportional to 1 over the square root of the mass. That's the same thing we just said on the previous slide, except we added the square root, and that square root just accounts for the fact that the velocity is squared in that kinetic energy equation. So twice as much velocity doesn't mean half as much mass, but bigger velocity does mean less mass. So the equation shows the ratio of the speed of gas A to gas B is going to be equal to the ratio of the mass of B over the mass of A. Because they're inversely related, if A is on the top of one side, it's going to be on the bottom of the other, and vice versa. Whatever is on the bottom of one side is on the top of the other. This is the only equation that we're introducing. So that's Graham's law. I got 3 examples to illustrate how that works. First one is the easiest of the 3. Not too bad. We want to find the relative rate of diffusion for krypton and bromine. Relative rate of diffusion. In other words, how fast does krypton move compared to bromine? Does it move twice as fast? Does it move 3 times as fast? Does it move 2.5 times as fast? That's all that means. The rate of diffusion is talking about how fast it's moving, the speed or the velocity, and the fact that it's a relatively